This is the summary that's on the page, starting on page 2 of your polar graphing notes. We're going to summarize the things we've learned about polar graphs so far. First of all, limesons. All limesons have a period of 2 pi. It takes 2 pi radians to get the entire graph. Given the equation r equals a plus b sine of theta, we have a limeson without a loop when a is greater than b. And I'm going to put the absolute value of, because sometimes a or b could be negative numbers, but this is when that one is larger than the other. You'll recall that since sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, etc., looking at this little t-chart, when sine of theta is equal to 0, then we'll just be plotting a, whatever that number a is. So that's this point, these 2 points to the side on the graph. When when we do sine of pi over 2, that equals 1, and so the distance on the graph r would equal a plus b, and that would be this point at the top. And then when we're at 3 pi over 2, it'd be a minus b, and that would be the point at the bottom. Now, if a is less than b, so I think I did greater, yeah, when a is less than b, then when we do that 3 pi over 2 one, we get the loop. And so that creates the loop here when we're at 3 pi over 2. And then when the absolute value of a is equal to the absolute value of b, then a plus b is still the big difference, but then the 3 pi over 2 gives us 0, and we just get this point right on the pole. So at the bottom, you'll see a little summary of those things. Now that's just for sine with when sine is in the bulk of the graph is above the horizontal axis. So what about the other 3 situations, or all 4 situations here? So if we have r equals a plus b sine of theta, then that's symmetric with the y-axis or the vertical axis. So in other words, it looks the same on both sides. Here, actually, I'll draw it down here where it's easier. It looks the same on both sides of the vertical axis. When b is greater than 0, we're above the horizontal axis. When b equals less than 0, we're below the horizontal axis. For cosine, then we're symmetric with the x-axis or the horizontal axis, so it looks the same on both sides of the horizontal axis. When b is greater than 0, we're to the right. When b is less than 0, we're to the left. Remember that changing the sign of a doesn't change the graph, but it changes the direction in which the points are plotted. Okay, next page, we're looking now at circles and lines and roses. So circles, we have 2 different types of circles. We have the circles, when we have a cosine theta, we have a circle that's going through the pole, but it's either to the right or to the left of the vertical axis. So if a is greater than 0, it's to the right. If a is less than 0, it's to the left. And a equals the diameter of the circle. The period for these graphs is pi, because all of the points are in only 2 of the quadrants. When we have angles in the other 2 quadrants, they have negative radiuses, or radii, I guess, so they reflect back onto these points. So when cosine is negative, it reflects back into quadrants 1 and 4, and we just get all these points over again. For sine, we either have a graph that's going up, because that's where sine is positive, or down. When we have a negative a, then it flips it upside down. So a is greater than 0, a is less than 0. Once again, a is the diameter, and the period is pi. Then if r equals a, that's the circle centered at the origin. The period is 2 pi, because notice that we have points located in all 4 quadrants. Then a is the radius here. For lines, a secant theta will, in rectangular form, will give us the line x equals a, which is a vertical line through the point A on that axis. So the radius is equal to A. The period for these are just pi. Once again, notice that we only have points in quadrants 1 and 2, or 1 and 4, which is where cosine, the reciprocal of secant, is positive. When cosine is negative, then we get negative values for r that reflect back over here and just repeat the line in the same spot. For cosecant, the rectangular form is y equals a. These are horizontal lines, and this is a units in this direction, a units up, and the period is pi. When we have theta equals a, that's where theta is always the same, but we just change values. We can just put in any value for r that we want. So whatever the angle is, it's just going to be a diagonal line through the pole, and the angle is a. So whatever that a is the angle. And the period really is not applicable here because we're only dealing with one angle. Okay. For the characteristics of the roses, we have both a sine b theta or a cosine b theta. I left the theta off the notes for its sine. You might want to put that in there, right there. The center of all of the roses is at the pole, 0, 0. The length of the petals is a. Number of petals depends on whether b is even or odd. If b is even, it's 2 times b, and the period is 2 pi. If b is odd, the number of petals is b, and the period is pi, and then it just repeats itself. For the tip of the first petal, if we're dealing with a sine graph, the tip of the first petal occurs when theta is equal to pi over 2b, because when we multiply pi over 2b times b, we get pi over 2, and that's the largest value for sine. The largest value for cosine occurs when theta is 0. So we're always going to get a petal at on the positive horizontal axis. Here we'll have a petal that's rotated. Now, rotating polar graphs, very easy to rotate. All you do is to rotate, let me start with a capital letter here, I guess, to rotate c radians, so we're just going to use that to represent the number of radians, c radians in the positive direction, we just subtract c from theta. Subtract c from theta. So an example would be if we have the equation r equals 3 cosine theta, to rotate, we would say r is equal to 3 cosine, got my little line through theta there, of theta minus pi over 3, for example. Okay. Advantages of graphing in polar form, 3 different things. Number 1, some curves that aren't functions in rectangular form are functions in polar form. Okay, some curves that aren't functions in, I'll just say xy form, are functions in polar form. For example, circles. Sorry for making you watch me write here. So circles, for example. I'll just put example here, circles. Number 2, easier to rotate graphs than in rectangular form. So it's easier to rotate the graphs in polar form than in rectangular form. And once again, I'll just write xy form because it's faster. And the third thing is some equations are simpler in polar form. Once again, the circles would be a good example. Are simpler. For some reason, I'm getting some hesitation on my writing here. Okay, some equations are simpler in polar form. So that's the end of our summary of polar graphs.